machine learning. Before coming to Chicago, he was at Georgia Tech, and before that he was at Yahoo Research. He received his PhD from Yale and his undergraduate degree from Princeton. And he has served on steering committees and as associate editors, editorial board of various journals and conferences, as well as program chair of conferences. His research has been funded by National Science Foundation and Department of Defense, as well as he has earned several rewards. This is our pleasure to have you here, Lev, and thank you very much for taking the time, and I look forward to your talk today.
Thank you for inviting me, and it's nice to virtually meet all of you. Since we want to leave time for questions, I want to start right away, but I just want to have a disclaimer that this work, this is recent work in an interesting line of work about differential privacy, but machine learning and all sorts of other things. And it talks about connections between all these interesting fields, which is why I find it so fascinating. But I can't really talk about my results without putting them into a broader context and explaining a little bit about all these other fields. And so it's very possible that I'm only going to get to my results at the very end. But if what you take away from this talk is not my work, but about these new connections in which it is possible to do important and interesting research, I'll be more than happy. And so I might not get to our results at the end, and you know, that's somewhat on purpose and somewhat because of the time limit. Okay. So the talk is labeled Differential Privacy, Adaptive Data Analysis, and Free Speedups from Sampling. And it's with Ben Fish, who is a postdoc at MSR Montreal and Mila, and Ben Rubinstein, who's at Melbourne. Ben Fish was my PhD student, and now he's a postdoc, and he's on the market this year. And so I would be remiss if I didn't tell you he's fantastic. And if you have any openings, you should hire him. Okay. Okay. And the paper that this work, you know, you can read about in detail is Sampling Without Compromising Accuracy in Adaptive Data Analysis in Alt 2020 of this year. Okay, now let's talk about the problem that this work is situated in. And that is that data sets are often reused, and that's not usually a thing that's allowed to happen. In particular, you get the problem of overfitting when you do this. And this has many names because this problem appears in many fields: false discovery, garden of forking paths, p-hacking. I'm sure you've heard of a variant of it. And the problem can be summarized in a thing that people do all the time. And that is, you have a data set. This is your validation set. I'm assuming you guys can see the hand still. Okay, let me know if you can't see this hand. Okay, so there's a validation set, and that's kind of the data set you're, so you could be training on something and validated on something, or you could be just training all in one thing. It doesn't matter. You have some data set and you train a neural network. And in training a neural network, you're already selecting the best parameters for a neural network given the structure of the neural network. And so you're adapting. That sort of adaptation is fine. But then let's say on the validation set, your error is not good enough. And so you remake your neural network. You modify the structure, et cetera, and then you measure loss again. From traditional machine learning, we have no guarantees whatever anymore. Once you look at your data set, you're not allowed to change the class of model where you're, what you're doing, right? And so this is called adaptivity. We're using a data set to choose a new model, or to kind of do something, like if you say, I'm only optimizing decision trees on my data set, that's okay. But if you use decision trees and then you look at your data and like, I don't like how decision trees did, let's use boosting or whatever, not okay anymore. Okay, and everyone kind of knows this. And so adaptivity, the fact that we can't actually, in practice, redraw data sets for free, makes it difficult to generalize. Okay, and so Moritz Hart, who's one of the leaders of this field, he's a faculty at Berkeley, he just has this nice little picture, just what is static versus adaptive. Static is you have a method, you use the data and you make an outcome. And adaptive is the method looks at the data, you get an outcome, and that changes your method. And you want to be in this loop, ever improving your method. So this is, the right-hand side is what adaptivity kind of is. What's not adaptive, by the way, this is another thing that people might think is adaptive, but that's not what we call adaptivity for our purposes. Is if you have a method and you use it on data and you don't like the outcome, if you change the method but then use new data, etc., that's not adaptive, because you are not adapting to a data set, and instead you're drawing new data sets. So drawing new data sets is more or less okay. I mean, of course, you have your own problems with continually redrawing data sets, because, for example, there's some probability you'll have a mismeasurement on a given data set, and if you keep drawing a new data set, testing the same method, maybe eventually your method will look like it's doing better on the new data set than it really is, but we can control for this sort of thing by drawing large enough data sets, etc. So this is not what I mean by adaptivity. Okay. And so we want to be able to answer queries adaptively on a fixed data set without having to assume anything about the nature of the adaptivity. So we don't want to say, well, you can change your algorithm, but not by too much. Or without assuming anything about the complexity class from which our queries into the data come from, like bounded VC dimension. So let me make it clear. Queries could be, I mean, we'll define queries later, but what is the error rate of my hypothesis is a perfectly fine query. And so measuring the error rates of various things that you've trained can very well be thought of as a query, but queries could be other things, just any question onto the data. And hopefully many of you are familiar with the traditional way of being able to ask lots of questions into a data set without having to draw new data. And the traditional way is to measure something about the complexity of your questions. So like if your questions or if your hypothesis class has bounded VC dimension or bounded Rademacher complexity or bounded size or bounded something, then very often we have these Occam-Reyzin times theorems that are like at the foundation of learning theory that let us just say, okay, well then you can ask all these questions at once and things are fine. And so the goal of this work is not to assume anything of this form. Okay. And okay, so this framework was formalized in I guess a field called adaptive data analysis, and this was by a group of superstars: Cynthia Dwork, Moritz Hart, Aaron Roth, Tonian Patasi. I'm sure I'm forgetting some people. And this was a paper in Science, and the idea is they were trying to convince scientists to adopt a new view of kind of learning from data. And that is because, of course, in science, you gather data, you spend a lot of money on it, right? And then very often you keep testing different hypotheses on your data set, and you can fool yourself into thinking you have a false discovery. This is partly why so many scientific results don't replicate. And so this was actually picked up by mainstream publications like cover all of science, and yet somehow this is not as well known within the theoretical computer science community or the machine learning community as I think it should be. And so this is their framework. There's an unknown distribution, and there's a data set that's drawn, the green thing, from this unknown distribution. And you have a mechanism, this is like a question answering system, that has to answer questions using the sample. And now you have an adversary that's attacking the system by asking questions. And the mechanism has to use the sample. The mechanism doesn't know the distribution. The mechanism just knows the sample and has to answer the questions from the sample that it has. And the point is that the answers have to be not necessarily true in the sample, though that would be nice, but they have to be true in this unknown distribution. And the adversary cracks the mechanism if at a certain time it asks a question that the mechanism can't answer correctly according to the unknown distribution. So a question is some function from data, like what is the error rate of my hypothesis, or what fraction of the data have this property, or anything like that. And once the mechanism is unable to answer questions truthfully according to this unknown distribution from which it has a sample, we say the adversary has broken the mechanism. And so the goal here is to design mechanisms that are as robust as possible to adversaries trying to break them. Now, the motivation never had an adversary, right? The motivation of this problem had you just trying to learn from data. But the viewpoint adaptive data analysis makes is that you are your own adversary. That is, as Richard Feynman said, the easiest person to fool is yourself. And so the idea is you, in practice, would implement both sides of this. The adversary is actually the learner, and then the mechanism is that something that's sitting around the data set that's protecting the learner from itself, protecting from the learner from making false discoveries. And the whole goal of this field is how many queries can we answer and how long does it take to answer the queries as a function of, for example, the size of the sample we have, etc. Okay, now I know you guys are not used to asking questions in the middle of these talks, as I was told, but maybe here would be one exception, because if someone is lost about like where we are or what we're doing, you know, this may be a good time. So I'll pause for 10 seconds and let anyone ask a question about what the goal of this is, if there is one.
So I have a clarification question. So suppose, let's say you are trying to learn, I don't know, maybe a circuit or a decision tree based on this data that represent this. Now, when adversary asks a question, does it mean that the adversary is going to give a decision tree and then say, is this the correct decision tree? And then the mechanism is supposed to answer yes or no? Is that a valid way of thinking?
Well, okay, so right. So this is an okay question to ask, although the mechanism has a labeled data set. It doesn't have a notion of correctness, but maybe you can ask, does the decision tree predict the labels correctly? Okay. Or it might ask like, what is the error rate of this decision tree on this data set? Or if there is some model of a decision tree that the mechanism has that's encoded in the data, you can ask such a question.
So the mechanism only looks at this data set, but it might be doing some inference based on the data set, and then based on that, it could still answer the adversary.
Yeah. The mechanism is allowed to do whatever it wants. It just fails when it no longer reflects reality, which is in the distribution.
Okay, thank you.
Okay, and okay, so now what are queries? So this probably is just good to formulate. So a query is just any function from the distribution onto, let's say, the real line or into real numbers, on which, and the mechanism is just trying to return function values that are close to the function when evaluated on this distribution. And for example, but of course, the mechanism doesn't have access to the distribution, so it needs to estimate it. So like a very typical thing, like the most famous type of query is called a statistical query. And so the function is specified from the data onto 0, 1. And then the mechanism, for example, can look at the sample and just average the query value on the entire sample and return the sum of all the queries on the sample divided by 1 size of S. And so not only can the mechanism do this, but the expectation of Q of S is Q of D. Does that make sense?
Well, so can I ask you a question? What is X? X is a subcode of D?
No, X is the domain of the data.
Okay.
Sorry, that's the typical machine learning notation. So data is always on X. And
D is on X.
Labels,
okay.
We're going to stick the labels into X also.
Right. So D is on X. Okay.
Mm-hmm. And okay, so statistical queries are some of the more basic queries. I mean, there are more basic queries you can formulate, but actually statistical queries are kind of very simple to understand. They're like point-wise queries that you can average over a data set. They're very well defined in a distribution, but actually they're super duper powerful. And so there's been a series of work. This is another thing that's not known as well as it should be. And I've recently written a survey on statistical queries because I want to preach to the world about how cool they are. And that is that statistical queries actually capture pretty much every method that we have. So any algorithm that we have, we could, if we really wanted to, phrase it as a series of statistical queries on a data set and then updates just based on the answers to statistical queries. And so most methods that we have for learning, and actually not just learning, can be implemented via SQ. And it's not like a theorem that's true for just all the methods or something. It's more like there's been a series of work for each individual method to try to figure out how to make it runnable through statistical queries. And so gradient descent is a clear example. You can ask for gradients and move in the direction for gradients and ask your queries like, what is the gradient here? What is the gradient here? Expectation maximization, support vector machines. Boosting was a really interesting result. You can actually boost without reweighing distribution on specific examples. Linear and convex optimization, MC simulated annealing, etc. It's actually really surprising how many methods have been converted into this framework. And actually, one big spiel that I have in my research is that in order to make progress in machine learning theory, we actually need to design non-statistical query methods, because statistical query methods also have some limitations. And we are very hard pressed to figure out anything that's not statistical query. We have basically two techniques that are not statistical queries. One is hashing, which doesn't get you very much in machine learning, and the other is Gaussian elimination, which gets you a little bit, but also not so much. And we are at a loss kind of to think of anything else, basically. Okay, so so what are the queries we can consider? Well, we consider things like counting queries. So counting query asks what proportion of the data satisfies a given property. And it's specified as from data onto 0, 1. So so this is kind of like a limited statistical query where you either satisfy the property or you don't. And then here the question is, here's a property, what fraction of the data satisfies it? And there's some true expectation distribution. And basically these counting queries are just the right way to think about statistical queries. We also think of things like optimization queries. This is a more powerful thing and more used in adaptive, well, they're kind of popular these days. An optimization query is the following. What you give is, sorry, I can't see my own slides because of the, okay, I think I moved the thing. Okay, so what you give to an optimization query is like a class of functions, and the optimization query tells you what parameter optimizes over these questions over the distribution. And so maybe I can give you an example. So maybe your functions could be like loss functions with a minimum, and an optimization query asks where is this function minimized, and the min point would be returned by an optimization query. So now there are statistical query methods to implement optimization queries, but you can actually ask about optimization queries on their own right. So this, I'm just trying to give you the sort of queries that people could ask. There's something called a low sensitivity query. A low sensitivity query is if any function that doesn't change too much, if any one data point is changed. That's another query you might want to consider. And that's actually more powerful than a statistical query because a statistical query is a big average over data set points, and a low sensitivity query is just any query that doesn't change. So an average is one of them, but you could have other things. Of course, you could just say, hey, we're not going to think about any restriction of queries. We would just say query, but it's very hard to prove theorems about just any query. In fact, we know we couldn't. Okay. And now, so if you're familiar with the PAC learning framework, right? In PAC learning, this is supervised machine learning, you have like an error and a confidence parameter. And in adaptive data analysis, you have something very similar. You have an alpha and beta parameter. So in PAC, we call them epsilon delta. In adaptive data analysis, we call them alpha beta. And so we say a mechanism is alpha beta accurate on a distribution if for every single query, the biggest miss is bounded by alpha with probability at least 1 minus beta. So alpha bounds the difference between an answer returned and the true answer in a distribution. and 1 minus beta. Beta is like the failure probability or bound in the failure probability. Okay, sorry. And now Zoom has blocked my slides again. Sorry. Okay, and so a typical question you might ask is how many samples n does it take to answer k adaptive queries efficiently with alpha?
I have a question. So, sorry, what is A here? What is A?
A is the answer. So every query QI is the mechanism answers with answer AI.
And what the script is?
And now the question is, what is the biggest difference between the answer that the mechanism gives and the true answer?
And your probability is over M, which is mechanism.
The probability is over any randomness the mechanism uses, and any randomness that's in the data. So like, because the mechanism draws a sample.
The script A is then the
right. It's also right. I'm sorry. So it's also the script A is the adversary. So the adversary can also use randomness. So the probability is taken of over all the randomness in anyone in anyone.
I see. So A is asking the query.
Yeah, A is the adversary asking the query QI.
I see.
AI is generated by the mechanism as the answer to QI. And the question is and then each query has a true answer QI of D.
Right.
And the question is, what is the biggest mistake? Like as in and so we want to bound the biggest mistake in advance by some parameter alpha. We want to fail with probability no more than beta. And this is just like pack learning. And the question is, how many samples did the mechanism need to draw?
So I'm kind of confused about your adversary. You're not seems to be specified. So with respect to a fixed adversary, is that
right? So we assume nothing about the adversary
for all adversaries.
So we need this to be for all adversaries, right? So I didn't, of course, quantify all this. There exists a mechanism such that for all adversaries, it's like a pack thing with there exists an algorithm such that for any distribution, etc.
So for all adversaries, this has to be true to call it a mechanism to call it alpha beta.
Yes, that's right.
Great, thank you. Yep.
And thank you. Okay, and so the reason we ask like how many samples does it take to answer k queries? Well, because there's always some way to do it with enough samples. Here's how. For each query, right? Each one query, you know how many samples you need, right? And that is to be within alpha with probability 1 minus beta, what you need is like 1 over alpha squared queries times log 1 over beta. And then by union bound, if you draw basically k times that amount, you can just divide your data set into independent pieces, and each independent piece would be used to answer each query. And so you could always answer queries accurately if you redraw data for each query, and then you could just say, oh, if I had this huge amount of data, I could just simulate or redraw the data. The point is, can we do much better? Can we actually reuse data? Can we be adaptive, but not shoot ourselves in the foot? Okay. This is kind of like a theoretical framework for this. Again, unfortunately, I won't get into too much of the theorem proving within this framework, but again, I think it's so important to know about the fact that this exists, that I don't mind, wasting time from my own results or using time from my own results in order to teach you about this. Okay. Okay, now, what would a standard machine learning algorithm do? Well, on PAC, there's basically one method, and that's called ERM. And what it basically does is on a query queue, it returns the value of the query on S. And in some sense, well, it depends on what type of query it is, but in general, forget about even ERM. If someone asks, like, what is the error rate of this hypothesis? The best estimate is to compute its empirical error and return that. And then you use bounds to say the empirical error is close to the true error. But for adaptive data analysis, answering queries truthfully turns out to be suboptimal. As in, if each time the mechanism would do this just for QI of D, draw a sample, and average over the sample, well, first of all, I mean, you don't get to do that for every type of query, but let's say we have a query where this is like an okay thing to do, like a statistical query. It's gonna be the case that we're gonna need to use a lot more samples to get alpha beta accuracy than if we were a little smarter. Okay, does everyone understand this claim? Not the proof of it, just the claim. Okay, and And one of the coolest adaptations, one of the coolest explanation or illustrations of this phenomenon is an attack on a leaderboard. So a leaderboard is something that's used right now in like every data science competition. You have a holdout set of predictions and you give a training set, and then people submit. So it's like Kaggle or something. People submit their classifiers, and what you do is you tell them what their error rate is on the holdout set. And the person who has the smallest error in the holdout set, let's say, wins. And so Avram Blum and Moritz Hart thought of this really cute attack called the boosting attack on a holdout set. So imagine you have a holdout set of n data points. What you could do is you can pick k vectors uniformly at random. Each vector just gives a random classification of the data. And so then you get k losses, which are what is my error rate on the data. And then you just find the set of them that do better than random guessing. And then as your predictor, you use the majority of the ones that did better than random guessing. And now we might try to analyze what in the world this method would do. But before I do that, this is kind of like a theoretical construct. So let me give a picture. So, okay. So the leaderboard, let's say, has a holdout set of n examples. That's on the right, on the upper. These are the columns, okay? And so what this attack would do is it would pick k different hypotheses. Each one just gives a random label for each example. And now the leaderboard would have to answer all of these and tell them what is the accuracy of each of these k vectors. And let's say the leaderboard is answering honestly. So let's say it says the error rate of the first guy is 0.55, of the next guy is 0.48, then 0.53, etc. Okay, so what the leaderboard can do is it can block out into gray all the guys that are red. Red means they're doing worse than random guessing. And so it could only consider the ones that are green, the ones that did better than random guessing. And then choose a vector U star that is the majority of the ones that did better than random guessing. So the majority for X1 would be 0, 1, and 0. So the majority of that is 0. But like here, for example, the 1, 1, and 0, the majority here is 1. And so it could afterwards use U star as its predictor. Now notice, if U star is a good predictor, we have broken this adaptive data analysis. Why? Well, U1 through UK are random vectors. And U star is a majority of a subset of random vectors. It should do better as well as random. It's true on the true distribution, it should have error rate 1/2. Now, if on the sample it has error rate better than 1/2, that means we broke adaptivity. And sure enough, Avram Blum and Moritz Hart showed that with at least constant probability, the loss of this U star vector is 1/2 minus square root k over n, which is a problem because as k grows, you're separated more and more from 1/2 as the number of random vectors grows. The reason it's a problem is because if you were to redraw data for each response, you would continue to have 50% error as you should. But if you do this, if you give actual naive responses, if you actually tell people their true error from this random attack, this U star vector's error rate will go down and down and down to 0, even though you've learned nothing. And actually, this has been a problem for a while. And this is why leaderboards now, one way to handle this problem is now they have like a training set, a holdout set, and then a double holdout set where you're evaluated on the secret thing that nobody knows. So if you overfit to the holdout set, that's kind of like your problem. But your true ranking is evaluated on something that nobody's ever seen. But of course, this makes the leaderboard kind of really silly because it's giving up-to-date answers on who's in first, who's on second, who's on third, on a holdout set that's not reflective of reality at all. And you can get into first place on such a leaderboard without having anything on the true holdout set. Moreover, if they actually gave true rankings on the true holdouts, that would leak information and open them up again to attack. And so the way leaderboards often deal with this now is that they report a leaderboard that has no bearing on reality. Okay, hopefully everyone understands a little bit of what I said. Okay, so now here comes the main idea. And I think it's one of the most beautiful ideas I've seen in learning theory, even though it's a very simple idea. This idea is the following. We're going to put a privacy layer around the data. And on query Q, we're not going to return Q of S. We're going to return a private version of Q of S. And the intuitive idea is that an algorithm that cannot learn the data itself will not overfit to the data. And so for this, something called a transfer theorem is used. And the idea is that there's some notion of stability. And this notion of stability applies to algorithms whose output doesn't change too much when the inputs change by a little. And you can actually prove something called a transfer theorem that says that stable algorithms generalize better than non-stable algorithms. Now, most of you have probably not heard of stability, but there's actually a very specific notion of stability that probably everyone has heard of by now, and that is differential privacy. And so the most important and popular notion of stability is differential privacy, and here's what differential privacy is. Differential privacy says that a mechanism is epsilon delta private if, when it gets two samples that differ on just one point, their responses differ by not too much. They don't differ by a multiplicative factor of e to the epsilon and an additive factor of delta. What I mean by their probabilities don't differ is the probability it outputs any given response is similar for the two mechanisms. And so, yeah, I guess I could talk a little bit about differential privacy, like why this is e to the epsilon, and like why is one of the factors in the exponent and one just a linear term. And the reason is this is so that you can compose privacy parameters. But instead, I'll just give you an example. So let's say S is some data set, and a differential private mechanism has a distribution of responses over the data set. So the x-axis is outcomes, and the y-axis is probability. So this red curve represents the probability of giving any outcome. And now we change the data set from the red one to the blue data set, which differs just by one example. And so now you have a different blue probability of outcomes. And what differential privacy says is the following, that for any outcome, so for any value here on this x-axis, the two y values are not too different. The probability of any one outcome is going to be approximately the same if the data set didn't change too much. And the intuitive motivation for this is that if the probability of any given outcome doesn't change by too much, if the data set is just changed by one example, well then people should be incentivized to participate in the data set because their participation doesn't change the probability over outcomes anyway. And now you could basically, now we have all sorts of algorithms that just are there. Differential privacy is a very mature field, and we know how to give differentially private responses in leaderboards and anything so there are a lot of queries for which we know how to do differentially private responses. And so if the queries are of the form of which we can answer differential privately, now the boosting attack doesn't work anymore, for example. And so the blue line is the boosting attack. Now you can get a little bit better than a half for technical reasons, which I don't want to go into. But you're not really going to improve. And that is because the differentially private responses, they're close to the true errors, but they're hiding the data in a way that the majority doesn't give you anything. So this is one example of differential privacy saving you from an attack. Now, what's a standard differential privacy mechanism for answering statistical queries. Well, what you do is you return the true answer of the query plus some noise that you might want to add. And they use Laplace noise, which is a little more concentrated around the mean than normal noise. And I mean, there are different theorems you can prove, but basically Laplace noise gives you a good trade-off between how inaccurate this makes the query and how much privacy is still preserved. So for example, Laplace noise is, why do we use Laplace noise instead of the normal distribution? Well, because the normal distribution makes the query less accurate, right? It's a little less concentrated. And so, of course, the normal distribution would work. It just doesn't give you as good of a trade-off as Laplace noise. So we use Laplace noise. And so this mechanism is nice because on the one hand, it's accurate in the sample, it's private for statistical queries, and it's sufficient to guarantee accuracy on the distribution. As in, you get a transfer theorem, like the type I mentioned. Okay, now I'm kind of rushing through this part because I want to talk a little bit about the flavor of my results, but I also know we don't have much time. And so if at this point you're now going to follow along, but you followed before, you already learned kind of, I think, something very cool. Okay.
So I have a question.
Yes.
So before we go forward, I think since there were a few questions, maybe it might be okay to go until a little bit later too.
Okay, well, we could do it however
yeah.
you want. I could also just wrap up quickly and leave more time for questions now. Like I can finish in 5 minutes. I don't know.
Yeah, whichever way you want to do it.
I really don't have a preference. So just ask a question. Don't ask a question. I'm happy.
Am I supposed to ask a question or no question?
I don't know. So
go ahead, please. Go ahead, please. Yeah.
No, I was just wondering, just if you go back to the previous slide. So the goal here is not to give the adversary enough information so that even if he asks many questions, he still don't reveal any information. So it looks to me that, is that the goal of the mechanism?
Okay, so the goal is to be accurate. So the goal in adaptive data analysis is to be accurate for as long as possible. And a mechanism for doing this is to answer differentially privately, which means that you're answering accurately, but with some noise. And the whole trade-off is how much noise can we add such that we're still alpha accurate, alpha beta accurate. So the idea is we can't add too much noise because then we'll lose our accuracy guarantee. And if we add too little noise, the adversary will adapt quickly, right? So the question is, in some sense, if you're going to use differential privacy for this, like how do you set the parameters and stuff? You could also not be differentially private. You could do something else and still remain alpha beta accurately. So differential privacy is just one mechanism for answering statistical queries, for example, but it's not necessarily the only one. It's just a good one. Let me go on.
Yep.
Again, this all gets very confusing and technical, that like anything, right? Like the model is clean and cool, and then the results, like, okay. And so there are all sorts of known results. So for example, we know, for example, how to do low sensitivity queries and statistical queries in root K over alpha squared. And we know that this is at least tight in K. We know how to do convex optimization queries in root KD, where D is the dimension of the space, over alpha squared. We know how to do like hypothesis testing, etc. Let me skip that part. But here's an interesting thing. All of these queries, all of these mechanisms take linear time per query. So if you have a big data set, the way all of the known mechanisms do it is they evaluate the query truthfully on the entire data set, and then they add noise. And if you have a giant, huge data set of like, I don't know, like data on 30 million people, this is actually doesn't correspond to what people do in practice. And so here's a summary of our results. So we basically take this column where Basili et al., who are the main people who did this before, and what we do is we basically improve our dependencies on K, let's say. I mean, we improve some other stuff, but like, for example, we usually go from square root of K to log K, or from K to log K. And how do we do this? So K is, again, the number of queries asked. And let me just go back to our idea, and maybe I'll stop there, because the idea itself is really cool. So instead of answering the query truthfully on the entire data set and adding noise, our idea is the following. Let's just sample some small number, L points, uniformly at random, and give either the true answer for them or add noise to that answer. Let's just consider answering truthfully on this. And so you could see in expectation, this should all work, right? So answering truthfully on a small subset should be about the same as answering truthfully on the whole set, should be about the same as answering on the whole set plus noise. But interestingly enough, we can prove exactly the same transfer theorem on the sampling technique. And let me just give you the proof idea, the main idea, because I think the main idea is an obvious thing that you can remember, and everything else is stuff you can look up in the paper. The main idea is the following. If instead of giving true answers and adding noise, what you do is you subsample your data. Subsampling your data set loses accuracy, right? So if I have 1,000 examples and instead I just give a true answer on 5 examples, this loses accuracy just because I'm not using the whole data set. On the other hand, that adds privacy, because I don't need noise in some sense to now hide most of the data. If I subsample just 5 data points and report the true answer on the 5 data points, most of the data points haven't even participated in the subsample on which I've used to compute my answer. And so this subsampling technique intuitively gives you worse estimators, but on the other hand, gives you more privacy, because most data don't participate in the subsample. And now if you think about what a transfer theorem requires that goes from differential privacy to stability, right? The transfer into, from differential privacy into adaptive data analysis, the transfer would get better as you have more privacy, but worse as you have less accuracy. And so this technique basically makes your accuracy worse, but your privacy better. And we can prove that those two exactly cancel out, and that you get subsampling for free. So you can speed up algorithms dependence on the number of queries to linear per query to logarithmic per query. You need logarithmic because of a Hofting type bound. You have to still be within reasonable bounds for all the queries. So your sample has to be of size logarithmic in the total number of queries asked. But otherwise, you can get per query exponential speedups precisely because everything that you lose in accuracy, you're gaining in privacy for this transfer from differential privacy onto adaptive data analysis. And there are really cool applications to convex optimization, which I'll skip, except for to mention one, and that is there's this thing called stochastic gradient descent. Stochastic gradient descent is like gradient descent to do optimization, except for instead of computing the true gradient on the entire data set, what you do is you pick a random example and you compute the true gradient on just a random example. Well, what this work does is it says, actually, this gives a framework for just saying that this is an okay thing to do. Because stochastic gradient descent, or stochastic block gradient descent, where you take a few examples and compute true gradients instead of an everything, exactly has this trade-off where you lose accuracy in your estimate of the gradient, but what you gain is actually privacy. What you gain is the ability to not overfit. And our analysis gives a completely different, like our results just give a completely different analysis of why stochastic block gradient descent or stochastic gradient descent works. You can view stochastic gradient descent as something that just boosts the privacy of a stable algorithm or a differentially private algorithm in order to give you the accuracy. And why do people use stochastic gradient descent? Precisely because they want faster convergence to the optimum. And so this is another example of how this framework explains something that was only understood through a very specialized theorem before. I can see that I'm at 12:50 and I'm now going to get to sampling counting queries, but let me just say that faster adaptive data analysis is not only possible, but like can be done very quickly. It has applications to convex optimization. And there are even things you can do with constant numbers of samples that is meaningful. And another thing is this kind of like, some people have commented on this work that it kind of combines property testing and adaptive data analysis. The idea is you're looking at a very small part of your data and you're drawing conclusions that are important. And somehow this, because privacy gets you so much here and compensates for loss of accuracy, this is a really neat way where you can get free speedups. It's also the case that we still don't know the optimal dependence on any of, well, not on any, but on many of the parameters, we still don't know the optimal dependence. For example, we have 1 over alpha squared dependence, but only 1 over alpha lower bounds for a lot of the problems. And so there's still a lot of interesting work to be done in this field and a lot of work to design practical algorithms, et cetera. And so, just a lot of interesting kind of things, at least intuitively, that are happening here. And so I wanted to talk about this. I'm sorry I didn't get to talk about the details of my work, but we started 5 minutes late and we want to end early. And so I think I'll just stop here, and hopefully you can check out my paper if you're interested. Thank you so much.
Thank you very much. Thank you for your talk. And I think we still have time for a few questions.
Hi, Lev. So this is Kevin.
Hi, Kevin.
Liu. I'm just curious. When you do this subsampling, do you have basically? Can you tell me a little bit more detail how the subsampling was done?
Well, right. So the analysis. Okay, so this is theoretical work, right? So the analysis is just for a uniformly random subsample of the data, and actually we've done 2 analyses, one for with replacement and one.
Lev, you're on mute.
I don't think I'm muted, but can you hear me now?
Yeah.
I think you were fine.
Okay, so our theoretical analysis is for subsampling where so the theorem gives you how many samples you need, and you can either take them from the data set with replacement uniformly at random or without replacement uniformly at random. We have theorems that both ways are okay to do. And then actually we got into like a whole rabbit hole about what is the complexity of subsampling with or without replacement. And in different cases, it's different. And what you should do is you should do the subsampling that's actually faster, because we have a proof that both ways are okay. And then there's actually a technical reason why we still have to add Laplace noise, even to the subsample. So our algorithm does a uniformly random, either with or without replacement subsample, and then we need to add Laplace noise, even to the subsample. And the reason is because basically, there's this notion of natural privacy, where if right, there's some uncertainty introduced by just taking a subsample, but the uncertainty goes away as the true result of the query approaches 0 or 1. Like if a query is deterministically 0, right, the subsample will return 0 regardless of which points participate in the subsample, and that actually violates differential privacy. So the reason you need to still add Laplace noise is because of these border cases, which you can actually handle in much cleaner ways. But basically, the theorem is very straightforward. You sample with or without replacement uniformly at random, and you return your true answer on the subsample.
Right, and the subsampling, it seems to me it's sort of like a log of k or something. You improved the previous linear dependence to some. So does that mean that you only need like a some log order number of samples to do that?
That's a very good question. So we actually, right, this is a point I did not have time to address. We don't reduce the size of the underlying data set. The size of the underlying data set actually has to stay the same. And so there is a linear dependence on K in the size of the data set, and we still need that for our theorem. What we get to do is just make faster per query evaluations. But the theorems will fall apart if you actually take a smaller sample overall.
Okay.
And so it's only to speed up
Yeah.
queries, not to make anything more sample efficient.
I see. Yeah, very interesting. I'm going to check the paper for more details. Thank you.
We still have time for a couple more questions if you would like to use the microphone, please.
If not, that's okay too. I won't be offended.
Looks like that a lot of the questions were asked during the talk itself. Thank you. Thank you again. I think this was a very helpful introduction to this new area that where we don't have any individuals working in this area in our group yet, but this will be an interesting area to explore. And thank you again for taking the time at such a short notice to give this talk. I appreciated that very much.
Thank you for inviting me. This was fun.
Yeah.
Goodbye, everyone.
Thank you very much, and goodbye, everyone. This concludes the TADS seminar for today. Thank you.
Thank you.
Thank you.